Konstantin Aleshkin, who is presently in IPNU in Tokyo, who will speak about Quasimaps theory. So, please.
Could All right. Thank you very much for introduction. Yeah, it's nice to be back here. It's nice to be in Boris' room. So I was his a student when I was here. So yeah, today I'm going to talk about mathematical theory of GLSMs. And yeah, while preparing this talk, I decided actually to swap around the two parts of the talk I had because I realized it's going to be too long, and then I'll probably want to start with a less technical part. So maybe I'll say it like this. So mirror symmetry and central charges. For abelian GLSM. So what I'm going to talk about is a mathematical theory of GLSM, and so most of the results I'm going to talk are actually work in progress, but are about the mathematical theory. But I'll also try to connect them to the interesting and relevant questions in the physics of GLSM. Right? So what is a GLSM for me, right? So it stands for gauge linear sigma model, and then in physics, it's a theory that that's been out for over the 30 years, and the data that determines the GLSM is the following data. So, and maybe for this part I'll make like a little dictionary. So. So the first piece of data is a finite dimensional vector space, C to some power R, complex vector space. So in physics, this is R chiral superfields. And then second piece of data is a choice of a subgroup inside GLV, inside of the linear group acting on this vector space, which I'll call gamma. So it's a complex reductive algebraic group, which for most of this talk is actually going to be a torus. So in physics, this is gauge group plus R symmetry. So there is a reason why it's convenient to talk about both of them at the same time. So third piece of data is the choice of a character of this group, some non-trivial character, which I'll call chi. So surjective character. And then I'll denote this C star as C star subscript omega, because there will be several C stars in my talk, just to distinguish them. And another piece of notation in this part is that, so the kernel of this character, this is a normal subgroup in gamma, which I'll call G. And so in physics terminology, so G is the gauge group. And then this gives, well, there is not always a splitting between gauge group and our symmetry group in this setting, but Here's the data. So another piece of data is a superpotential. So it's a holomorphic function on V, a polynomial in fact, such that it transforms under the group gamma with respect to this character. So if little gamma denotes an element in the big gamma, then I require that W of gamma of X is chi of gamma, so the value of this character on this group element, applied to or multiplied by W of X. So in particular, this means that W is G invariant. And then it has, so in the physical terminology, it has R charge, non-trivial R charge. So so in final piece of data is a choice of a stability condition, zeta. So this is going to be a rational character of R charge 2. Well, so so what I wrote here is that W transforms under this action with respect to this character. Well, in physics, usually you take a splitting of this gamma as a well, there is no, it's not always possible, but let's say it's possible to take a splitting of this as a G and C star, and this C star is the R charge. And then the normalization in physics works in this way, so that this actually, how should I say it? So this character is square of the fundamental character of this additional C star. Make sense?
Yeah. I was just wondering because you were making addition is
right. So yeah, please feel free to ask questions because everyone's background, I guess, is different. So, right. So choice of a rational G character, and then in physics, this is the choice of the Fourier-Illoux constant. All right. So given this data, we can define the particular manifold of variety, which I'll call X. And so there are two ways to define this variety. So one way is using the geometric invariant theory. So given a choice of a G character, there is a way to define some open subspace of V of zeta semi-stable points. And then X is a quotient of this semi-stable locus inside V by the group G. And then I use the brackets to mean the orbital quotient, because this could be an orbital. So they assume this is smooth orbital. And more symplectic geometrically, or physically, I guess, so we can have so if we have an algebraic reductive group, there is a compact subgroup, maximal compact subgroup. Well, and then the action of this subgroup on V is symplectic. So with the momentum map, mu, so is momentum map well, and then X by current theorem is the same as pre-image of zeta, of So this goes to the dual of the Lie algebra of of the compact group, right? And so in particular, zeta lives inside this dual of the Lie algebra. And then another way to write X is a Hamiltonian reduction, so it's a pre-image of a zeta under the moment map, quotient by the compact group. Mm-hmm. So zeta is this part of data, so it's a choice of right. Mm-hmm. And so this rational characters is the same as let's say maybe I should write it like this. So if we tensor this with R, we'll get exactly the Lie algebra, dual of the Lie algebra. Okay. Other questions? So now W, since W is G invariant, W descends to X. We shall denote by the same name. So it's a holomorphic function. And then both in physical and mathematical theory of GLSM, people are interested in the critical locus of this function. So let finally Z be the critical locus of W inside X, which is by definition substack where the differential of this vanishes. And so mathematically, so the theory of GLSM is a curve counting theory or enumerative theory of the Gromov-Witten type associated to this critical locus. And physically, well, physically Z is a vacuum manifold of the theory. Okay? And so when Z is smooth, when Z is an actual manifold, then this mathematical theory, for example, reproduces the Gromov-Witten theory of this manifold. But the interesting case is when Z is not smooth. And now I'll write some examples, which I have in mind. So first is my favorite example is a quintic threefold. In order to construct the GLSM that produces, so the quintic threefold is going to be the critical manifold associated to that. So in order to construct this, we use the following data. So we take our vector space to be C6. We consider 6 chiral superfields with coordinates x1 up to x5 and p. And then gamma is going to be C star squared. So, and I'll denote the charges of the action, or the weights of the action of gamma on C6 in this table. So the first copy of C star acts on axis by weight 1 and on P by weight minus 5. And then the second copy of C star acts by weight 0 on axis and by weight 1 on P. So, and then this table corresponds to the gauge group G. So this is G. And this part corresponds to our symmetry group. So in particular, in this case, the group gamma is split as a product of two copies of C star. So in particular, we can write if an element here is T1, T2, then chi of T1, T2 is just T2. So the superpotential is P times any quintic polynomial of X. Or rather, if we want our theory to be well behaved, we want it to be non-degenerate. So generic degree 5 polynomial. So finally, I have to tell you what zeta is. And there are two interesting choices. So gauge group is one-dimensional, just to start. So the choice of the stability parameter zeta, or the Fourier-Laplace variable, is just one-dimensional. So two choices. Zeta plus, which is positive, and zeta minus, which is negative. So well, both of them I'll just leave in Q, which is just a one-dimensional lattice of characters. So you might ask what happens if zeta is 0. Well, then this GIT quotient or this symplectic reduction is not going to be smooth. So, and let me briefly discuss what happens in both of these cases. So let's say in the first case, the corresponding X is going to be the total space of O minus 5 over P4, which is a total space of the canonical bundle over P4. So the way to see it is the stability condition forces all the x's to be non-zero. And then you take the quotient with respect to a C star, whose weights you can see in the first line. And so if you forget this P variable, you just get a P4, projecting space of dimension 4. And then this minus 5 adds a line bundle of degree minus 5. And so now what is Z? Well, dW is equal to dP times Q, phi of x, plus P times dQ phi of x. And so if this polynomial is not degenerate, the only way to satisfy the equation that dW is equal to 0 is when both P and this quintic polynomial vanish. So in particular, Z is going to be the common zero locus of these two equations, which is exactly the quintic inside P4. Questions about this one?
Just regarding the normalization of the charge, you said that you want the charge that from square root to be equal to 2.
Right, in the physical normalization. So here I'm just discussing kind of the mathematical side. So in physics, you want to put 2 here, right? But this is just a normalization, so.
Yeah.
So the second case, when z is negative, the stability condition tells you that P cannot be 0. And so you can use this C star to fix P equal to 1. And then what you get is C5 with coordinates x1 up to x5. And then again, a residual symmetry of order 5, because this has weight 5. And so the result is that x is going to be a quotient of C5 by a group of roots of order 5, so an orbifold. And the critical locus of W is going to be also given by the same equations. But in this case, this is actually going to be just, this is not going to be this equation because P has to be 1 in this case. So in this case, you can check that the critical locus is just going to be the origin. Okay? And so GLSM in general are very convenient both in physics and mathematics to study the relation between theories, different theories. In this case, we have two significantly different choices of stability condition, and they lead to two very different looking vacuum manifolds, let's say, and theories. And GLSM is a nice setting that allows to connect them. So there is a relation between 1 and 2 is called Landau-Ginzburg-Calabi-Yau correspondence. And there is a lot of literature about this, both in physical and mathematical side. Maybe in mathematics, in physics, I can just cite the original Witten's paper. In mathematics, there is a paper by Kyoda and Rowan about 2008, I want to say. So let me give another example. So I call this one extended quintic. So and it's certain extension of the first example. So for the vector space, we take now C8 with coordinates x1 up to x5, p, and then two additional coordinates u and v. We take the group gamma again to be C star squared. With the following weights of the action. So the weights of the first line are 1, 1, 1, 1, and minus 5 as in the first example. And then the weights on u and v are the opposite weights, 1 and minus 1. Whereas for the second line, which again will correspond to r charges, we'll take the following choice. It is going to be zeros on axis, 2 on p, and 1 on both u and v. So in this case, actually, the gauge group is not going to be just C star. Because of this particular rate distribution, it's actually going to be C star cross Z2. So the additional Z2 action will act on U and V by weight minus 1. And for the superpotential, okay, so the character, the gamma character, I'll use the same notation for the variable inside our group. It's going to be T2 squared. And for the superpotential, we can actually take a family of superpotentials. So the first part is going to be the old superpotential P times Q5 of X. But now we have two additional variables. And if you think about it a little, there is only one way to make this, to add something depending on u and v, such that it satisfies all the constraints. So in particular, you want your potential to be invariant with respect to the first line. So you want a combination of u times v. And then you want it to have the same weight with respect to the second line as this summand. So the only summand you can add is u times v.
Sorry, are you doing this that not to that inside another C star is not fully there?
Right. So let's see.
No, it's fine. I just don't understand.
So this is, you're right. So this is going to be precisely the Z2 inside this copy of C star that acts by -1 on U and V and by 1 on everything else. So maybe you can say that, yeah. Mm-hmm. So this is just the solution to this equation, right? And here I'll put a constant in front of this summand. So this example is actually very trivial if C is not 0. So if C is not 0, then, so I won't discuss in details X and Z because they're just a little more complicated. But you can show that Z, which is a critical locus of the superpotential, is isomorphic to the quintic inside P4. Maybe I'll write it Q5 of X equal to 0 inside P4. Up to some twist by the symmetry factor. So actually it's times point modulo mu2. And so the theory that we get is essentially the same as along the quintic case. But in the case where C equal to 0, this critical locus becomes singular. And the theory, or maybe I should say it like this. So the closed GLSM invariants of this extended quintic are related to open Gromov-Witten invariants of the quintic threefold. So this is in my paper with Melissa Liu, where we basically, yeah. So I haven't yet explained what the closed invariants are, but if you're familiar with Gromov-Witten theory, you can imagine you are counting maps of in this case just spheres or P1s. If you're algebraically minded into this critical locus in a particular way. And so the invariants that we get are related to the open invariants, open Gromov-Witten invariants of the regular quintic. So as in papers by Walcher, and then Walcher, Pandripanda, Salomon. Sure. Right. That's a good point. Thank you. So here you can have two choices of theta because, well, the character lattice of this group is also one-dimensional. And again, you have non-trivial smooth targets for positive values and for negative values. For positive values, you get, so this statement is true for the positive values. So for the negative values, you get something that is conjecture related to open FGRW invariants, but those are not yet defined. So we get some results in the negative values of zeta, but so maybe I should just write that. So this is true for zeta greater than 0. And then there are some conjectures for the case where z is negative. So the reason I provide this example without much details is to demonstrate that in GLSM, if you allow your, so we call X target space, if you allow your and Z the critical locus, or the vacuum manifold, if you allow your vacuum manifold to be singular, you can get some quite interesting connections with other theories, let's say open Gromov-Witten theory, or there are some other results how you can use GLSMs of genus 0 to produce some constraints for higher genus Gromov-Witten invariants. So there are a lot of interesting examples.
Could you give some information on why that is?
Right. So yeah, we tried to generalize something that is known in a different setting. So there is so-called open-closed correspondence for toric Calabi-Yau threefolds. So if you have a toric Calabi-Yau threefolds, you can also define Gromov-Witten theory. And then it has been conjectured for over 20 years and known for about 10 years in some generality, and then a few years in more generally, that the closed Gromov-Witten theory of toric Calabi-Yau threefolds is related to, open Gromov-Witten theory of Calabi-Yau threefolds, toric Calabi-Yau threefolds, is related to closed Gromov-Witten theory of particular Calabi-Yau fourfolds, which are obtained a certain extension. You can, so you can also think about Gromov-Witten theory in terms of GLSMs. If you do this, the toric open Gromov-Witten theory can be obtained by certain extension of the closed theory. And so we tried to do something similar in this case. So a little more geometrically, what happens is that so when you study this open Gromov-Witten theory, you choose a particular. So when you study open Gromov-Witten theory, you study surfaces with boundaries and maps of surfaces with boundaries, and you have to specify your boundary to lie on some Lagrangian. And so here in this works, they chose a very particular Lagrangian, which is a fixed locus of certain Z2 acting on the quintic threefold, which is called real quintic, this Z2 acts as some antiholomorphic involution. And so we try to engineer this Z2 symmetry to somehow to reproduce the computations you get in the invariants in the open sector. Mm-hmm. In this case, genus 0, yeah. So open closed correspondence is known only for genus 0, and I don't think it's believed to hold beyond that. I think even for it's just going to vanish. Exactly. That's the reason. That's the reason. But there is some way, there is some conjectural way to make it work if you just add some. If for invariants you twist your invariants by some Hodge classes, but yeah.
In your example, the Calabi-Yau threefold is common.
Yes.
Important?
Yes, because this is somehow. I mean, there are two things to it. So first of all, yeah, the open closed correspondence was only known for the toric case, and toric Calabi-Yaus are non-compact. So it's kind of the first case which is compact. And second of all is, you want some sort of compactness of the target space if you do some sort of curve counting. And in this case, you just start with a compact manifold. In the toric case, you put some symmetry to make it compact, or to make it equivalently compact. So you put some symmetry such that the fixed points of your symmetry groups are compact. So you always need some sort of compactness to make this theory work. It's like when you integrate something over a space, you want the space to be compact in some sense. All right. Other questions? All right. Then let me jump straight to the mirror symmetry for abelian GLSMs. I'll skip the quasimaps for now, since they're more technical. So, well, what I mean by abelian GLSM, I mean when the gauge group is abelian, and in particular gamma is abelian, and for simplicity, we take this group just to be a torus. Like in this case, this group gamma in this example is always just a torus. So it's C star to some power k. And then in this case, X is a toric DM stack, or toric orbifold. In the sense of Borisov, Chern, Smith. And so, well, for toric geometry, mirror symmetry obviously has been studied for decades, and people know a lot of results. But here I want to talk about some partial generalization of this of many mirror symmetry constructions to this setting. So in order to do this, I will construct a pair of two different GLSMs starting from some data. So let me talk about what the data is. And so the idea of the construction is by Patrick Clarke, or just Clark. So we'll start with data, which is very familiar to people who did some computation in toric geometry. But if you're not, I'll try to explain it for it to make sense. So we start with some finite rank abelian group, actually a free abelian group, so n. Just say just z to the power n. And then I'll denote m as its dual. And so consider the following data. So a collection of vectors inside n, vi's from 1 to r, and the collection of the same number of rational numbers, which I'll call zeta I tilde. And so this zeta should remind you of the stability parameter, because it will play a role as stability parameter in the construction. So those are just rational numbers. So now I want to define a space based on this data. So these vectors, they define a map from z to the power r to n, where ith basis vector goes to the R goes to Vi. And for simplicity, we assume that this map is surjective. And in particular, I can find the kernel of this map. So I'll call this kernel L, as some people do in toric geometry. So L is just, let's call this map V. So you get an exact sequence of abelian groups. You can tensor this exact sequence of abelian groups by C star to get exact sequence of tori. So, well, this becomes just a torus of dimension R, C star to the R. This becomes a torus of dimension N, and I use notations from toric geometry. So to call it just T. And then the kernel is also a torus. I call it G, because this will play a role of the gauge group in the construction of the GLSM. So now we define as X as a GIT quotient or a symplectic reduction of C to the power R, which is C to the R underlying this torus C star to the R. The quotient by G. So now I need to tell you what is zeta here. Well, zeta is constructed easily from these rational numbers. So another thing we can do with exact sequence, we can dualize it and tensor by Q. So what we get is Q to the R mapping to L check Q. Here we're going to get MQ, where M was dual of N. And this is nothing but the rational characters of this torus over here. And now, once we get a collection of R rational numbers in here, we can just map it to a rational co-character of G, rational character of G, zeta. And so this will define as a stability parameter. So if you are not familiar with this type of computations, it's probably too much to digest on the spot. But the upshot here is that this data, the collection of vectors inside a lattice define you a torus action on a vector space, which is almost a GIT quotient. And then this collection of rational numbers, which we can choose arbitrarily, this gives exactly the choice of the stability condition of a Liouville's parameter, or the character of this torus. So now I want to define the superpotential here, and I will start it by using a very similar piece of data. But maybe other questions before? Okay. So the other collection of data will be very symmetric to this one. And this is a collection of vectors inside the dual of N, which are called Wj, ranging from 1 to S. and also a collection of rational numbers for each of these vectors, which are called tj tilde. And the condition I'll impose is that, well, these vectors are from dual lattices, so we can take their scalar product. And the condition that I impose is that the vectors from the first set pair with vectors from the second set non-negatively. So vi pair with wj is non-negative for all I and j. So by this data, I can define a generic function on x in the following way. So define a function w naught from T, which is a torus inside X, to C by the following formula. So W naught of X, small x, is going to be a sum of S terms, X to the Wj. So what do I mean by that? So Wj is an element of M, which is a character lattice of the torus T. In other words, each Wj is just a function on the torus itself. So this is the function that it denotes. Or in coordinates, this is going to be this. And I also want to multiply this by some constant, and the constant is going to be the exponential of the constant that I chose here. And so under this condition, that this vector space very positively, this function, which is defined on the torus, actually extends to the partial computification of the torus, which is x. So under our assumption, W naught extends to the boundary, and we get a function from x to c. So now, starting with these two pieces of data, we get a manifold of the type that I described above and a function on it. So now we can guess how to get a mirror pair. You just change the roles of these two pieces of data. So to get a mirror pair, change the roles of n and m. In other words, we use the data of W and T to define x check verbatim the way I did here for x. And the data of V and zeta tilde to define a function. And so the statement is that these two pair of manifolds in a function are a mirror pair. Maybe I can write as a conjecture. Right. Right. They are, because so X is a compactification of the torus T, and X check is a compactification of the dual torus. So they're torus of the same dimension. Right. So R and S, they do not change the dimension of. So if you increase R, you also increase the rank of the gauge group. So the dimension of X does not change. So R is basically a number of torus divisors inside X. So you can make it bigger, but then it will say that it will tell that on the mirror you'll have more monomials for the mirror potential. Okay. So here, let's consider one example. A very simple example. So let both n and m be Z2. So a planar case. So that I can draw everything. Mm-hmm. Right, that's why I wrote it as a conjecture. So here, the point is that so far those are not even GLSM. Because if you choose the data like this, you won't even have the R symmetry. So you get a function, so you get a space with a function in it, but a priori there might not be any action on this space that scales your function. Right? So I'll comment on this later. How to make sure that both of them are GLSM, or at least one of them is GLSM. And then I can also make the conjecture more precise. So there are several statements you can make. And for me, the statement that I'm proving are mathematical statements about the state spaces, which I can construct, and about the central charges, which on the one side are going to be generating series of enumerative invariants. And on the other side, there's going to be some sort of oscillatory integrals. There could also be some homological mirror symmetry statement, but for now it's not clear. So, right. So consider a planar example with three vectors, v0, v1, v2. And then in the dual space, we will consider two vectors. So this is inside N, maybe tensor R. And the dual picture will have two vectors inside M, tensor R. So in this case, and you can take the corresponding arbitrary values of zeta and t. So in this case, X is going to be either KP2, sorry, KP1, so which is a total space of minus 2 over P1. So if you're familiar with toric geometry, this is a fan of that. And this will be the case if zeta tilde, I guess 0, minus zeta tilde 1 minus zeta tilde 2 is positive. Or it can be a quotient of C2 by me2 in the case when this expression is negative. So this is a baby case of the quintic, which is a quadric in P1. 2 points. So, and how do you construct a function from this? So the function will have two monomials because we have two vectors. And in the torus coordinate associated to this picture, the function will look like, guess x2 times x1 times exponential minus, t tilde 1, plus, this is 1 over x1, plus x1 e to the t tilde 2. Okay? And so what is going to be the mirror pair? Obtained from this data by considering a toric variety associated to this fun, and then function associated to this data. So x check is going to be, well, this is just an affine toric variety, but in this case, we actually have to take into account the symmetry factor. So this is going to be an orbifold of C2 by mu2, and there is no stability parameter. And W check is going to be a function with 3 monomials, and in the dual toric coordinates, it will look like this. Okay? So again, if you know some toric geometry, you might know that if you forget this is going to be just a mirror potential for P1. So this is some generalization of that. So I think I'm running low on time. So let me maybe briefly sum up the point that I was trying to make. So one point is that a priori, neither xw nor x check w check define a GLSM because of our symmetry. In other words, you only have a group G and you don't have a group gamma. And it is easy to fix this. So this so the way to do this is to require certain property for your function. So xw defines a GLSM if and only if if and only if we choose vectors wj in a certain way, there exists some vector which I call Vr, standing for R symmetry in N, such that it pairs with all the vectors wj is 1, if and only if x check is a toric Calabi-Yau manifold. And in particular, if you want a pair of models to be mirror to each other, they both have to be Calabi-Yau models. So if both x and x check are Calabi-Yau, then both models xw and xw check are GLSMs, and this is the only way this can be true. And the last thing I wanted to mention is that what this conjecture means and what can we actually prove. Mirror symmetry statement. So first of all, I didn't discuss what a state space associated to GLSM is, but you can imagine it's some sort of some sort of cohomology theory associated to such a pair. So we can have so we always assume that at least one of the pairs x w or x check w check is a GLSM. So this condition is satisfied. And then we can have partial results on isomorphism of state spaces. And then in the case when x is semi-positive, well, yeah, maybe I don't have time to say exactly what it is. Then we can prove the mirror theorem for central charges or a variation of Hodge structure statement of mirror symmetry. So yeah, I apologize, I don't have time to explain what that is, but I'm happy to answer any questions. Thank you for your attention.
Yeah, first related question a bit worse. Now, is mirror symmetry construction show that for a case that is complex?
Right.
We can also do it as
so this case is.
If you have some discrete scheme in the locus of W is not compact, does it work?
Right. So the target space X here is non-compact. This is KP1. So for the critical locus, the compactness, at least some sort of compactness is important for these statements. So I can say the following. So at least for now, the statements that we proved are the statements where we assume that the critical locus is compact. But I am certain that it is easy to generalize to the case of, let's say, when your GLSM is something like a Nakajima-Curie variety. So let's say when your critical locus is not compact, but there is some symmetry group acting on it, and then the fixed locus of this action is compact. So if you require some sort of compactness, equivariant compactness, or I don't know, like maybe you consider cohomology with compact support for the state space, you need some sort of compactness to, at least the method that I use requires some sort of compactness statement, but this can be generalized to be equivariant compact or maybe cohomology with compact support or something like that.
So if you have a mirror pair, can you use the enumerative geometry of the associated critical loci? Sorry, if you have a candidate mirror pair, can you decide whether it's a mirror pair by looking at the enumerative geometry of the associated critical loci? Is it enough?
Well, that depends on what you call a mirror pair, right? Because so that's why here I didn't formulate any precise statement. So we can prove the enumerative mirror symmetry in the sense, right? So we can compute the genus zero quasimap invariants on the one side, and then we can get a generating function, and then we can match it with the integral on the mirror pair under these conditions. These things we can match, right? So whether this extends to some stricter versions of mirror symmetry, let's say homological mirror symmetry, or maybe, I mean, it's not exactly stricter, it's just a different version, right? Or maybe to some more vague physical notion of equivalence of conformal theories. This is a question, right? So, I mean, there are a lot of reasons to believe that this is true, but again, there is no precise argument for that.
What is known about the enumerativity of these invariants?
Not much. So the status is the following. So mathematical theory of GLSM started to develop in 2015. there some invariants have been defined, but in a certain narrow sense. In particular, there were no in paper by Fajar's-1. So the invariants didn't form a cohomological field theory, if you know what that is. It basically means that only some invariants are defined, and then there is not enough structure to deduce others. And so there were papers from 2020, and then there is paper from this year, 2025, which claim to define general GLSM invariants. And in one statement, we have a very precise cohomological field theory statement. So that means that at least the definition is good enough to deduce all the invariants. In the second paper is not completely finished yet, so it's also, but it also looks promising. But from the computational viewpoint, very little is known. So we know that when the critical locus of W is smooth and W satisfies some other technical conditions, then the GLSM theory reproduces Gromov-Witten theory of this critical locus. Other than that, so yeah, there are some papers by Mark Shoemaker where he computes some invariants. There is paper of me and my collaborator where we compute some quasimap invariants, but not. There are actually some K-theoretic computations by Yalong Cao and his collaborators, but yeah, it's still in a very early stage.
But for example, for the Witten theory, it's the narrative, right?
So we can compute the G0 quasimap invariants for all abelian GLSMs at least, and hopefully for non-abelian as well. But this is just quasimaps yet. So we don't know, for example, the analog of stable map invariants, or we don't know higher genus invariants. But for the quasimaps, we like for all the examples that I presented today for quasimap invariants, again, I haven't defined what they are, but those are the simplest type of invariants. You can compute them. In fact, yeah, this part is proved by computing the invariants and matching them against the integrals.
Questions? Okay, let's take